Yeah. So hello guys, welcome to this second lecture on machine learning. I'll call it second lecture, but the first was just an introduction, and we will still recap on certain concepts we learned in the first lecture. So this is gonna be quite different from what we have done before. So just to recap, in the beginning of this program or this training, I mentioned certain skills which every data analyst or every data analyst is supposed to have. So first, you are supposed to learn programming. So a lot of people would tell you as a data analyst, maybe you are not supposed to learn programming, but I'm telling you, to excel in this field, you're supposed to learn programming. And the importance of programming is it will help you to automate a lot of things. So you can see from what we learned in the data cleaning pipeline, we now just have a functionality where we just one line of code, we can clean our data. So we have wrapped our all of our functionalities of cleaning our data, removing missing values, dealing with inconsistencies, dealing with duplicate values, and so on. We wrapped it into one function, what we called a pipeline. And with that pipeline, if we just call that pipeline, or if we just execute that pipeline using our data, we can do all the functionalities within that pipeline. So it makes things very easy and very simple. Whereas if you were using something like Excel, what you would do is whenever you have new data coming, you still need to do those tasks manually. You go to columns and try to remove duplicates and all of this, whereas now you can do this automatically, and that is the power of programming. We learned that first, yes, you need to learn programming. We chose Python programming. It's very important for people to understand why we chose Python. The main reason why we chose Python is a very simple programming language because it has a lot of inbuilt functionality already in the program. So for example, if you know, when we wanted to create data frames, we use the pandas library. We use the functionalities within the pandas library. When we wanted to create visualizations, we use the matplotlib and the seaborn library. So these are already functionalities which before you have to worry about how do I create how can I plot a histogram, but someone has already done that for you, and so you just use their functionality. For example, plt.hist, which where the hist functionality will help you to plot a histogram, or plt.plot, where the plot functionality will help you to plot a scattered plot. So using that is the main reason why we chose Python. So using Python, we have learned how to clean our data. Remember, we learned SQL on and that was to enable us to query a database to retrieve our data for analysis. We have used Python to learn to understand how to clean the data, how to prepare the data, transform the data, and also how to visualize the data in order to answer business questions. We also use Python for hypothesis testing. So yesterday during the drop-in, I showed you how we could test hypotheses to see if gender, is there a relationship, or does gender impact the severity of accidents, or is there a relationship between gender and the severity of accidents? So these are all things which a data analyst must know. You are required to know this. So you going for a job, or you collecting data for a research, and they assume that you already know this and you can actually clean the data, visualize the data, and answer business questions. One of the most powerful skills which a lot of people who are just simple data analysts, so there are a lot of data analysts that can just visualize data using tools like Tableau and Power BI, or even Excel. I told you Excel is very powerful, so we should never minimize the power of Excel. So people that can just analyze the data in Excel or using Power BI or these more interactive tools are still data analysts, but what takes you out of that domain of data analyst to a more technical data analyst is machine learning, or what we call predictive analytics. And so the lectures for the next 2 weeks will be focusing on machine learning. So we'll be learning the fundamentals of machine learning, the blueprint, the pipeline of how data is, what the steps you need to take to build a machine learning model and to evaluate your machine learning model. And what is machine learning? Last week we defined what machine learning is. So machine learning is simply using historical data to extract patterns which you can use to predict the nearest future. Remember, you are always trying to predict the nearest future. So you cannot take historical data and you want to predict what will happen in 10 years time. No, because the assumption you are making when you're building a machine learning model is that the historical patterns are most likely to occur in the nearest future. That's why when you have events like COVID or you have events like the financial crisis in 2008, all predictive models the performance of all predictive models drastically reduced because there was no pattern in their historical data which showed them that COVID will come. So the model did not know how to predict even weather conditions or stock prices or health outcomes. There was a crash in all machine learning and AI models. But the good thing is when this occurs, so you can imagine, because we are using historical data to make predictions of the nearest future, as as you go into the nearest future, you keep what we call retraining your model. So for example, what happened in COVID now, a lot of people have embedded that historical information now in their model. So they have taken their model again, taken the data of what happened in COVID and have embedded that information in their model. So it makes their model now more likely in case to consider aspects like COVID and to consider all of these different patterns. So that said, for the next, so the course will be structured in a very interactive manner. So similar to other courses, we have Q&As after concepts have been taught. But the way I would teach this machine learning is even within when I'm teaching different concepts within those concepts, I'll be having the interaction with the audience. So I'll be asking you questions, and we'll still have our Q&As, but we'll be having this this interactive Q&As within the concept so that we ensure that we have understood a particular concept before we move on, even though we will still have Q&As at the end of the lecture. So going straight to what we'll be learning today, we'll be learning machine learning. And I said machine learning using historical data. So you have captured data about, for example, if we're talking about health outcomes, you have patient data. You have captured data about all of the patients in a particular hospital. And obviously, if you're looking at a particular disease, for example, cancer, you have the patient, the dynamics, the characteristics of that patient, the age, his sex, where his nationality. You have all of those demographics. You also have measurements, health measurements like his blood pressure, his height, his weight, and you also have maybe um, um, clinical procedures which have been done on that patient. So if the patient went through maybe a cardiovascular procedure or certain procedures, you have information about that. And you have obviously the main outcome, which is the stage of the patient's cancer, or if the patient doesn't have cancer, or and so on and so forth. And using this information, people now can take this information and say, okay, let's see, using these historical patterns of people who have cancer and do not have cancer, take into consideration the dynamics, demographics, take into consideration the procedures that they have gone through while in the hospital, take into consideration their lifestyle. So if they drink, smoke, and whatever, take into consideration all of these things. Let's see if we can see any pattern within the data that we can use to identify. So using that pattern, if we can say, okay, this is the pattern that follows for someone to be able, someone who has cancer or someone who doesn't have cancer, and so on and so forth. And using that pattern, you would like now to predict in the nearest future the probability of if someone is going to have cancer. So imagine you have patients who do not have cancer. You use their data, you use their lifestyle, you use all of these demographics data, and you tell them, okay, there is this percent probability. You take into consideration your lifestyle and the patterns we found in other people who have had cancer, and have a similar pattern with your lifestyle. There is a 90% probability that you're going to have cancer, or there is a 10% probability you're not going to have cancer. So we're predicting the nearest future of this health outcome of these patients using historical data of other patients. So that is what machine learning is all about. So first, I've presented a basic flow of the machine learning process. So the machine learning is not separate from the data cleaning stages which we did. So you cannot just take data and start predicting and creating a model to predict. So you see from the diagram, I've labeled what we have done before is what I've labeled in green. So we collected the data. You can collect the data from a stakeholder. You can query a database to collect your data. And we did cleaning of the data and modeling of the data, transformation of the data. You still need to do that before you start your machine learning. And before you start your machine learning, you split that data into randomly into a training set and a test set. I'll explain why this is important. So you split it into a training set and a test set. So normally you split the data, you take 80% random, a random sample of your data, 80%, you keep that 80% of your data, which you use to train your model, and you use the remaining 20% to test the model after you have created the model. So that's 80% which you have kept for training. You use that 80%. First of all, you have to select a model based on your problem. So there are different problems require different models. So you select your model, and the basic concept is to start with a simple model. So don't start developing, trying to use very complex models. You have heard of maybe a very complex convolutional neural network or a transformer, and you are excited and no. So you always start small. So you start with a simple decision tree or linear regression, a simple model, and take into consideration the performance you are getting from the test sets. Remember, you're training the data, you're training your model with the training data, and you're testing your model with the test data set. So you select a simple model, you train that model using the training data set, you evaluate it on the test data set, and depending on the performance, I'll teach you how to measure performance and which techniques to use to measure your performance. So the techniques again depend on the problem. So depending on the performance, if the performance, for example, if you are interested in accuracy, if your accuracy is below an acceptable range, remember the acceptable range is domain specific. So for health outcomes, if you want to predict someone who will have cancer in health domains, they may be very strict that the model must reach a certain percentage of accuracy before they deploy this model, because it's so, you can imagine the detrimental the effect it can have on people's emotions if you tell someone that there is a probability you're going to have cancer, and later on the person discover he doesn't, he never could have cancer. So imagine you gave the person a false positive, or you told the person he will have cancer, but so you can have the person's lifestyle or the person's feelings or the emotions can really be affected if you predict wrongly. Or in terms of finance, if you're predicting fraud, you want the model to be very accurate, because you know the financial consequences if you make a wrong prediction. If you saw a transaction and you said, okay, this transaction is not fraudulent, and it becomes fraudulent, you can imagine the financial consequences on customers. So certain domains will require very high accuracies as their acceptable accuracy, while other domains, maybe if you are just using your model for information, maybe a human resource department that wants to predict the probability of an employee leaving his company. I think we have that kind of data set in our list of data sets. So you want to predict if an employee will leave, take into consideration certain historical patterns you have seen in other employees that leave or stay. So imagine you in that case you will not be interested in maybe 100% accuracy, because there is no actual, because the information you are using is not, is for the human resource to create policies on how to maybe encourage people not to leave. So you are not looking at 100% accuracy, 80% accuracy, even a 70% accuracy in such a domain will still be acceptable, because what you are using it for is different from things like fraud and healthcare and so on and so forth. So when you get to whatever your domain, your company, or you decides is acceptable, then you can, you interpret the model. And what do we mean by interpreting the model? You look at which features in your data set have the highest impact on the outcome. So in healthcare, you look at what are the features that are driving someone to have cancer, or in fraud, you look at what are the features that are most important when you want to predict fraudulent activities. Human resource, you look at what are the features about the employees' day-to-day work life that can influence them leaving a company. And that's what we call interpreting the model. When you interpret the model, when you understand these factors, so you already know from what I've said, you already can see the importance of interpreting the model, because you can use this now to drive decisions, right? If you discover that someone's lifestyle, maybe them smoking, has a high probability for cancer, then even in your citizens, you can now limit the amount of alcohol or the amount of cigarettes that come into that country, to limit the amount of cancer you get in your community, and so on and so forth. After you interpret the model, if you have understood the factors which you use in decision making, you now deploy the model for doing prediction. So you start using the model and you monitor the model, right? What we mean by monitoring the model is you start looking at outcomes. If you see that, for example, your model has started behaving not as you expected, you may now want to retrain the model with new data. So imagine you have used the model for 3 months, and maybe you have now recruited so many, you are in your peak where you have recruited so many employees. You may want to retrain your data using this new vast data set you have, so that the model can capture more in underlying patterns. So that is the whole entire pipeline of machine learning. So we'll go in details into each element of the machine learning pipeline. So first we'll start with obviously splitting the data, selecting the model, training the data, evaluating the data, and so on and so forth. So going to that, um, so the first thing is, as I said, the machine learning elements. As I said, you need to understand the type of machine learning or the type of problem you are facing, right? And in order for you to be able to decide which model to use and which model to not to use, that is a big element of the machine learning pipeline. So when you get your data, you need to understand your data to know what the problem is and what is the outcome of your problem. And if your data has labeled, remember last week we discussed about labeled data and unlabeled data. I'll still go into detail when I'm talking about type of machine learning. Then after that, you split your data, as I said, you select your model. We'll learn what we call model parameters. These are the key aspects of the model. This is what is optimized. This is what changes for the model's performance to improve or reduce. So a model is, so the first thing you have to understand about when we are talking about a model, it's simply a mathematical equation. So machine learning, everything you have been hearing, AI, everything you hear about, these are mathematical equations. And what is an equation? An equation is similar to what we learned in Python, what we call a function, right? And what is a function? A function or an equation takes in inputs and spits out output. So you take in a certain value and you return the computation of that value using the equation to output an outcome. So when you say y is equal to 2x, which is an equation, a mathematical equation, which also we can say it's a function, x is the input while y is the output, right? So if you have if y is equal to 2x, if you put in the input of 1, so if x is equal to 1, y will be equal to 2. So you have put in 1, what you are expecting to get for y will be 2. So that is a mathematical equation. So if you have y is equal to 2x, you will be trying to optimize that value to. So 2 is the constant, is what you can change. X is a variable, so you cannot change x. X depends on the data. Y depends on the data. What you can change is that constant 2. So what a machine learning simply is doing is trying to change that value of 2. So it will try y is equal to 1x and see if y, the values you're getting for y is close to the actual values you are expecting for y, or if it's not close, it will say, okay, let's leave 1 and change that 1, y is equal to 1x to y is equal to 2x, and so on and so forth. I'll explain that, but it's very important when you always hear about machine learning, do not think about, people will say it's a machine, that it's simply a mathematical equation. And in that mathematical equation, you are trying to optimize the parameters which are the constants within that mathematical equation. You keep changing those parameters which are the constants until you get the best equation, where when you put in an x, you will get an expected y. So if you, for example, today it's raining, if there was an equation to predict the weather for today, which it was an equation, I'll expect, if I put in the date of today, I'll expect to get sunny, right? If it's sunny today. But if I put in the date of today and I get raining and I realize today was sunny, then I know that equation is not correct. So I'll need to optimize that equation so that whenever I put in the date of today, whatever date, I will get whatever the expected weather was on that day. So that is what we call optimizing the model, and that's what we call parameters. You are changing that constant within a mathematical equation, and I'll show you that. So after you have optimized your model, as I said, you have to evaluate your model, and there are so many different evaluation, what we call evaluation metrics, which are just evaluation functions that you can use to evaluate your model depending on your problem of your models. If you're doing a classification problem, you can use accuracy. I'll explain to you what a classification problem is. If you're doing a regression problem, you can use things like mean squared error, mean absolute error, and I'll explain you what a regression problem is. After you've evaluated your model using these accuracies or root mean squared errors or the error functions, using the performance of the model, you will know if your model is overfitting or underfitting. And I'll explain to you what overfitting and underfitting is. And take into consideration whichever you discover your model is doing, if it's overfitting, there are certain things you can follow to improve the performance. You never want your model to overfit or underfit. You want your model to perform good. And I'll explain that, what I mean by good. Then there are ways now which you can optimize the model. What we mean by optimize the model is that you are improving the accuracy or the error, or reducing the error. So you're not improving the error, you are reducing the error or increasing the accuracy, and you're ensuring that your model is not overfitting or underfitting. When you get to that stage where your error is acceptable, your accuracy acceptable, your model is not overfitting or underfitting, then you can use your model and you can start interpreting what your model is telling you about the features, the inputs. So that is basically what a machine learning is all about. So the first thing is, as I said, we need to determine what type of machine learning, what is the problem? What is the problem we are trying to solve? So you get your data. Last week, we discussed there are two types of machine learning problems. There is what we call a supervised machine learning problem, and there's what we call an unsupervised machine learning problem. Supervised machine learning is when we have the outcome within our historical data. So if, for example, in the cancer, if you have historical lifestyle data about patients, and you have if that patient has cancer or not, and your outcome is cancer, and you, for each of your patients, you know that they have cancer or they do not have cancer, then you will say your model is labeled because you have inputs, which are the patient's characteristics or the lifestyle or procedures that have been done to the patient, and you have the outcome, which is cancer. You know the outcome. So for each patient, you know the outcome. If in case you, for example, if we go to Cameroon and we go to a particular hospital, and let's say we just go to their database, and in this hospital they have been keeping records of their patients, but they have not been keeping outcomes. If their patient had malaria, they have not been keeping it. So they have not been saying keeping outcomes if their patient had malaria, because maybe because this was written in the book. So when a patient has malaria, instead of putting it in the system, they wrote in the patient's book. So in their system, they have everything about the patient. They have the patient's demographics, they have the patient's lifestyle, but they don't have any outcome. They don't know if the patient had malaria. They don't know if that patient has cancer. They don't know if that patient has any other disease. So in that case, we don't have a label for the data. So we have the inputs, the features of the patient, but we don't have the outcome. In that case, we say our data is unlabeled. And when our data is labeled, our machine learning is, we use what we call supervised machine learning, because we have inputs and we have we have an outcome, and we are trying to look for the patterns within the inputs that we can use to predict the outcome. When we don't have when our data is unlabeled, so we don't have the labels, we don't know the outcome, we have what we call unsupervised learning. This is a more difficult part of machine learning, because with this, you'll be finding patterns in the input data, but you do not know what those patterns relate to. So you can imagine the patient's data, you get clusters. So you can say, when you analyze that patient's data where you don't know any outcome of the patients, you can find that a certain group of patients, their data are similar, and a certain group of patients, they have similar patterns in their data. However, you do not know the outcome. So you don't know if the outcome for that group is actually cancer, or if the outcome for that group is actually malaria, or you don't know the outcome because you have just found patterns within the data. So what happens in unsupervised learning is, when you get these patterns, you now have to investigate further these patterns and create an assumption from the information you get within these patterns, right? So if you go now within these patterns and you discover one cluster are just clusters of people who smoke and people who drink, and another cluster is just cluster of people who do maybe yoga and maybe go to the gym every day. So what you have obtained is a pattern of maybe good healthcare or something, right? So you will label that data using so this will be an iteration between you, the doctor. So you go and see the doctor, you tell the doctor, this is what I have observed in this pattern. What do you think? Is it something with this observation, is it something a lot of cancer patients have, or is it something cancer patients do not have? And the doctor will be able to look at it and look at the patterns and the information you have gotten from that cluster. And someone asked me, how do you get the patterns and information? You use visualization. So you'll be looking at, you visualize what's happening within each cluster. So you do things like bar plots, everything we have learned. That is what you use to understand the pattern. So you look at visualizations within the different patterns, and you'll be seeing some discrepancy, right? So in one pattern, you see that the blood pressure is high. In another pattern, you see that the blood pressure is low. So you already know that this cluster has high people for high blood pressure, this other cluster has people for low blood pressure, and you do a lot of visualization, a lot of bar plots, histograms, and all of this, and you present that information to a domain expert like a doctor, and a doctor will look at it and say, wow, this all of these patterns we are seeing for this cluster, they are very similar to what we diagnose when someone comes for cancer. Then therefore you will now label that cluster as people who have cancer and label the other cluster as people who do not have cancer. So you have moved from a data that was not labeled to a data where you have used the patterns you have observed in the data to label the different clusters you have observed. In this course, for the next 2 weeks, we will focus just on supervised learning. For all the data sets I've provided, all the data sets have labels. And for our continuous professional development, I will challenge the learners to try to do unsupervised learning. So imagine you had the housing price data, right? You have the label, which is the or let's use yesterday we looked at the automobile data. You have a label which is the severity of the crash. I would challenge people to remove that feature called the severity later on, that doing your continuous professional development, and try to see if you can obtain the severity of accidents if you don't know the severity. So you have removed that feature from your data and you're using the data set without that severity, and try to see if you can obtain clusters of severity and non-severity. When you obtain those clusters, compare them with the actual severity of accidents. So for each accident, you know the severity, but you have removed the severity and you have considered that, okay, you don't know the severity of the accident. After you have obtained the clusters and you have labeled the data and you have said this accident is severe or not, compare it now with the actual severity data, which was the true severity, and see if your clusters are similar to what actually happened. And it will be interesting to see if the clustering approach which you will use can be able to extract again this severity or non-severity in accidents, similar to how we have extracted similar to the actual severity. We will not do unsupervised learning, but I'll put a lot of material again in the continuous professional development for people to try this. And again, I'm always available to have discussions on what you have observed when you have tried it, or if you have tried it, you're facing issues, I'll be there to help you. And if you can get unsupervised learning, you are even 6 steps ahead as a data. You are now a data scientist, because as I said, machine learning is even out of the scope of data analyst. Is you're moving to more intelligent analysis rather than exploratory analysis, which are the visualizations and the hypothesis testing. So yes, we'll focus on supervised learning. And under supervised learning, we have 2 types. We have regression analysis and we have classification analysis. For regression analysis, the data is continuous. So for example, housing prices is a regression problem because we have a continuous outcome. A numerical continuous outcome means a house can be $20,000, another house can be 50,000, another house can be 100,000, 200,000, and so it's on a continuous scale. So when you identify that your outcome is a continuous outcome, you need to use what we call regression machine learning models. So you'll be using regressors or what we call regression machine learning models. Classification is more for discrete categories. So if you are classifying, if you have a data set that says, for example, in the severity data, we had 3 types of severity: severe, moderate, and minor severity. That is a classification because it is categorized, right? So you're trying to classify accidents that will fall under these different categories. If you have another one in healthcare, someone has cancer and someone does not have cancer, that is a categorized outcome. rather than a continuous outcome, like trying to predict the grade of a student. The grade of a student is more continuous, right? The person can have 20, 30, 40 up to a certain bound. So it's more a continuous scale. Categorical outcomes, we use what we call classification machine learning models. So you see things like classifier or classification machine learning models. The good thing about machine learning is you don't need to, the machine learning models do not actually change. So for example, you have a decision tree, which if you are using, if your problem is regression, you use a decision tree regressor. If your problem is classification, you use a decision tree classifier. But the fundamentals of the decision tree will be the same even for the different problems. The only difference is that the outcome is continuous and one outcome is categorical. So you don't need to learn what decision trees for classifiers are and what decision trees for regressors are. The fundamentals of how decision trees work will be the same for these different machine learning approaches. So you don't need to learn the different ones. So you just learn decision trees and you know that the outcome would of a regressor will be continuous, while the outcome of a classifier will be categorical. But you learn the fundamentals of decision trees. Similar to linear regression, you learn the fundamentals of linear regression. The principles of linear regression will be similar to logistic regression, but the outcome will be, one will be a continuous and one will be categorical, and so on and so forth. So that is the first thing. So when you understand your data, you understand the outcome of your data. So you know that your data is labeled, you know that you have to use a supervised learning approach. You know your data has a continuous outcome, you know you have to use a regression approach. Then you move forward to choosing your machine learning model. As I said, these are the simplest and the most basic machine learning models. You have linear regressions, you have decision trees, and you have random forest. There are many more out there. So when this take into consideration what you observe in the evaluation of your model, you can now say, okay, maybe random forests are not capturing the patterns very well because there are you need a more complex model. Then you research on the more complex model, you see extreme trees, you see gradient boosting. So you can just ask Google, for example, I've discovered my random forest model is not, oh, ChatGPT, I've discovered my random forest model is underfitting, so it's not performing as expected, or is overfitting, it's whatever. How, which other model can I explore? So you tell ChatGPT what you have observed in your evaluation. You tell ChatGPT, for example, the model you have used, and ChatGPT will be able to guide you. If you found out that the model is this, you can explore this other model and this other model. Then you can ask ChatGPT, how do I use this other model? And obviously there will be a functionality within Python for you to use that other model. Remember, these models, we are not writing the models. The good thing about Python is Python already has functionalities embedded within it for us to just use these models. But I still want to be able to teach you what is embedded within those models so that you understand the whole concept of machine learning. In the using, you will not use that complexity, you will just use the functionality, but it's always important for you to understand what these models represent. So that said, I've already said this. So supervised learning, you have inputs, you have an outcome, and you are trying, as I said, the model is a function, is a mathematical equation. You are trying to, the goal is to create, is to find a function or a mathematical equation that will accurately map inputs to their correct output. That is the overall goal. But this will take is this is what it will, that is what we call machine learning, right? It will keep going through your data to find that optimal function that can map inputs to outcomes. So that said, again, you need to choose your type of model. In our this course, will be focusing um, on supervised learning. So I've just given you a step-by-step process of what happens in the entire machine learning pipeline. So I've given you an example. So as I said, the goal is to find a function, f of x, which is a mathematical equation that maps the input. So I've created, so in this exercise, please pay close attention to the data. So I've given you a sample data called, so the data has just one input and one output. Remember, most of our data have multiple inputs and one output, but this data I'm giving for simplicity has just one input, which is the R studied, and we want to see if there is, if we know that this person has studied for 20 hours, we can predict the score that the person will have in a particular course. So this is the data we have collected. So we have gone for 5 students in that course. After they have scored their exams, after their exams, we have gone and asked each of those students, how many hours did you take to study? So for this first student, the student told us he took 1 hour. The second student said he took 2 hours, 3 hours, 4 hours, 5 hours, and we have seen the scores of those students. We have seen that, okay, obviously we already see that there is a linear relationship, right? Then as the number of hours increase, we see that the score increases. If you plotted a scattered plot, or if you did like a linear, remember our linear regression, that line, you would have seen that there is some form of a linear regression, because I can already see that an increase in the hours leads to an increase in the score. But you have found that relationship, there's a linear relation, but now you want to build a model that would tell any student that if you study 6 hours, this is what you should be expecting to have, so that students already know that, okay, if I want to have 100%, this is the amount of hours I need to study. Or some students, for me, there was a time in my education, in my life, where I wasn't very interested in having 100%, right? I just wanted to pass, just be above the, what they call the distinction in the UK. The distinction is 70%. So I was just like, okay, if I have 71%, I have my distinction, and that's what's important for me. So someone may be interested in that score, in that amount of hours that will lead them to a distinction. They are not interested in 100%. They just need the number of hours, and that is where we want to build our model using this historical data to find a function that will best fit this historical data. So the function is fitting by the historical data, and we'll use that function which has best fitted this historical data to make predictions for the nearest outcome. Remember, the nearest outcome, the nearest future, sorry. Why? Because in the as further goes, we now see, imagine Professor Professor Henry can testify with me. For example, the way students were performing 3 years ago is totally different from now, because obviously they have ChatGPT. So you cannot use your data to predict performance 5 years ago with the same, a model to predict performance 5 years ago. You cannot use that model now, because students now have different sorts of tools they use to their advantage. So students that may not even study that much again can still perform very high, because they have tools that can assist them. So you have to always understand that it's for the nearest future, and you don't have to rely on the machine learning. The machine learning model has to rely on your intelligence. So as the person who built the machine learning model, if you discover things have changed in your domain, retrain your model. The machine learning model is, you are retraining, the machine learning model is as dumb as you make it, right? So you, as the expert in the domain, if you discover something has changed in that domain, go back to your machine learning model and retrain your machine learning model. Your machine learning model cannot retrain itself. There's other models, what we call reinforcement learning, which is a different part of machine learning, which can actually learn different patterns while it's predicting. But this machine learning we're talking about, you need to actually retrain your model when you observe things. So do not let machine learning to be in control. Control what you want the machine learning model to do, right? So you need to be involved. We always say there should be that human in the loop aspect of machine learning. So first, as I said, it's an equation. So imagine this is the simple equation we have. So we have, in this, we have an equation where we are trying to find the best f of x. F of x is the equation we want to optimize. X is that input of that equation. So x in our case is our R studied. F of x is the prediction of the score. So f of x, we know the real score, which is y. So y is the real score. That is the score that actually happened in our historical data when somebody studied for 1 hour. So when somebody studied for 1 hour, the x was 1, the y was 50. But we are trying to create a function called f of x to predict the score. So we are taking x as the input and we are trying to get a predicted score called f of x. And our equation is mx plus b. So there are two elements. This is the equation. All machine learning models will not be mx plus b. Mx plus b is the simplest machine learning. So you can, it's just a line. So when you learn the equation of a line, the equation of a line is y is equal to mx plus b. It's just a line. So we are looking at trying to fit a line in our model. When machine learning models become more complex, they do not plot, the f of x will not be mx plus b, it may be mx to the power 3. Why? Because when you square x, the line, it changes from a line to more of a curvy kind of maybe sigmoid function and so on and so forth. Why will it become complex? Because maybe the pattern is not as straight, cannot be obtained from a straight line. So you start using more complex mathematical equation. And that's where people, if you've heard of neural networks are simply still equations, but instead of mx, you have m to the x to the power 7 or x to the power 20. The equation is more complex, so that you are no longer using a line to predict the outcome. You are now using something like a sigmoid function. You are using a more complex mathematical equation. So a simple mathematical equation is generally a line, and a line is what we call a linear regression. So you are trying to plot a line. If I really it would have been really good if I plotted these hours, this data, so that you see the relationship. If I did a scattered plot and I put a line within it, I would have done that, but unfortunately I didn't do that, so pardon me. So in this line, as I said, the x is the input. So the x is not what you are trying to optimize. The x is the input. You are trying to optimize m and b. These are constants. So you're trying to change these values of m and b to ensure that fx, the values you get for fx, will be close to y. So for example, when a machine learning model starts, the algorithm randomly gives that equation random values of m and b, just random values. That is how the machine learning starts its optimization. So in this case, our m, let's assume we give it a random value of m equals 5 and we give b equals 0. So our fx will be 5x because b is 0 and m is 5. So that is the first equation our model will start with. We'll just start with a random value of the constant m and a random value of b. It starts with that random value and it does the first, it does the predictions, right? So you take 1 and put it f of in here. So 1, f of x, f of 1 will become what? F of 1 will be 5, right? Because 1 is 5. So f of 1 is 5 because x is 1. So I've written that here. So if you look at the blue down here, I've written the predicted scores. So when f of x, when we have m equals 5 and b equals 0, so our equation is f of x is equal to 5. When x is 1, we have f of x is 5. When x is 2, 2 times 5, we have 10. When f is 3, 3 times 5, we have 15, 20, and 25. So this is the values of the first version of our model. We call it the initial model, the first version of our model. So what do? You have gotten these predictions. The machine learning now goes now and say, okay, let's find how close this our model f of x, how close is it to the actual, what actually happened. Remember, we have historical data of what actually happened. So we actually know the scores. So we'll go, and that is what we call evaluating our model. We want to calculate an error, how bad our model is or how good our model is. So a simple error will be that, okay, we will see the difference between y and f of x in each of these scenarios, and we'll add that difference to see the total error of the model. Yes, a good hands up has been there, which is good. No. So correct. That is very good question, David. So B will not always be 0. This is the first initialization. So we have just randomly, B could be 10, B could be any number. So the first initialization is we can give M to be 0 and B to be 5. In this example, I have given the first initialization. I've given M to be 5 and B to be 0 for this example, for this first initialization. What influences B number? Nothing will influence. So you what will influence the change of the B number would be the error, right? So first, just imagine you gave B 1, and so just imagine this as an initialization. So we have our model, our equation is mx plus b. The algorithm will give M a random number and give B a random number. So in this case, in this example, I have given this first, I've given B 5, I've given M 5, I've given B 5. I could have still, do you also document this initial starting? Exactly. So Koge, what is happening? You are not in charge. I'm teaching you what is going on when you will be using the machine learning algorithm. Is that functionality, the machine learning will do it on its own. So you are not in charge. Yes. So, but the people who created that algorithm, this is what they do. But I am teaching you so that you understand what is happening in the functionalities you are using, so you don't use them blindly. So if someone asks, if you go for an interview, you go somewhere and someone asks you, how does a machine learning work, a model work? You can be able to explain that this is how a machine learning model works. It works by first giving a mathematical equation, some random values, checking the error of that first initialized function, and trying to improve the values of M and B so that the error reduces. That is what happens in a machine learning model. But when you will be using that machine learning model, you will not have to worry about that, because within the functionality of in Python, the algorithm will be doing that automatically for you. You will not be doing that. It's not you, David. You are not the person that will come and say M should be 5 and B to be 0. But no, that is what will be done, will be happening within the functionality you'll be using as a machine learning model. But as getting to this field, it is important you understand what is happening within. For example, yesterday we did chi-square test. We used the functionality of chi-square test within to calculate our statistical significance. Within that functionality, a lot of mathematical equation is going on. We did not bother about that complexity. We just say, okay, we use chi-square test and we'll look at the p-value chi-square test will give us to interpret our result. Another person who was teaching that chi-square test in a mathematics class would have told the people, would have taught those people exactly what is happening in that chi-square functionality. So this is exactly what I'm doing. You'll be using the functionality, but I want to tell you what happens, how the model works. So first it will initialize, but you should not worry about that. You don't have to keep a record about that. All that complexity has been taken away from you by Python. So you just have to worry about understanding what that functionality is actually doing. So yes, we have our predicted values, which is our first initialization. Again, remember, David, you could have given M any value, given B any value. We are just we're just assuming, imagine M was 5 and B was 0. So this will be the first predicted value of this will be our first score. If we do the error of this score, so we take 50 minus 5, that is the error for the first student, it means the error is 45, right? It means it's far from what actually happened. So because the student had 50, this initial function predicted that the student will have 5. So the error is 45. We'll do that for all the students and we'll add up that error to see the overall error of the model. Assuming the overall error of this model is 1000, right? If, as I said, the error value or whatever you get, it will be acceptable by you. You determine if you want it to be acceptable. So if the error is very high, you'll be like, oh, this is what you look at. You say, oh wow, this is not a good model. I cannot use this model in the real world. I cannot give people this initial model for people to use because I have seen that it's actually predicting very far from the actual scores that happen. So let me change the values of M and B. The changing of the values of M and B will happen again. It's a mathematical operation called gradient descent. We will learn a little bit about this. It's very mathematical. You deal with derivatives. But let's assume that all of this gradient descent and optimization is still happening within that functionality. Let's assume after this first scenario, the model obviously found out that the error was high, and the model said, okay, I will change using its gradient descent functionality. It said, I will change the value of M to 15, and I'll still maintain B to be 0. Again, David, the model using the gradient descent, the value of B could have been something else. I'll show you how gradient descent works. The value of B can be something else, but we are just assuming for understanding sake that, let's say, the gradient descent has been applied to this data, but the new M, which will improve the performance of the model, is 15, and the new B, which will improve the performance of the model, they have said it should not change. Let's not change the value of B. After we have done this, so now our new function is not fx is equal to 5x anymore. Our new function is fx is equal to 15x, right? So we have left this model. The model has been optimized using gradient descent. Our new function is fx is equal to 15x. It takes that 15x. So this is the next prediction. It takes 15x. It takes 1. It says 15, 2, 30, 3, 45, 4, 60, 5, 75. Are you seeing what's happening now? Are you seeing that the predictions now are getting closer to the actual score that occurred? This was far. So the error here, if you calculate the error now using these new predicted values, you observe that the error will be lower than the error you got here, because obviously 15 now is closer to 50, 30 now is closer to 55, 45 now is closer to 65, and so on. So the error here will be lower. So it will continue this process of gradient descent, trying to change the M and change the B till it reaches a value of M and B where fx, the values it's getting for fx are very close to the actual y's. When it reaches that value of M and B where fx is very close to y, we say you have trained the model. So here we have trained a machine learning model. That is when the model has done this optimization multiple times. So this optimization can take about 20 iterations. So 20 iterations, meaning it will change M and B, check the error, go again, change M and B. It will be doing that. It can take about, sorry, not 20, it can take about 100 iterations of trying to find. So it's a very, what we call heuristic approach. Heuristic meaning you are using a mathematical equation, but you're changing the values of M and B, changing and seeing if it will change, is changing, and so on and so on and so forth. So when he has done that multiple times, it reaches what we call convergence. Convergence is when the using its gradient descent, let's say the gradient descent, the best value after it did its gradient descent, let's say the value of M was 20 and the value of B was 0, for example. It's just an example. The next iteration, it changed the value of M to, using the gradient descent algorithm, it changed the value of M to 21 and the value of B to 1, for example. And it realizes the error doesn't change again. So you are now changing that M and B using this gradient descent, but you're now realizing the error is no longer changing that much. Because remember here, if you calculate the error between this and this, you see that there's a significant difference. So the error changed drastically. You keep optimizing this function, changing the values of m and b until you reach a point where even if you change m and even if you change b slightly, the error doesn't change anymore. That point is what we call a convergence point. So that point you say, okay, there's no need for me to keep training the model or trying to change M and B. Remember, you always be changing M and B slightly. You will not be changing M and B. In this case, I changed M from 5 to 15. Why? Because the error was large, right? When you get closer to Y, when f of x is getting closer to Y, you'll be changing M slighter. So you'll be changing M maybe from 15, you just change it to 15.5. B, you just change B to 1 and so on and so forth. And you reach a point where the error is not changing. So if the error is 25, when you change it, the error becomes 24.9. You change it, the error becomes 25.1. So the error is just within a certain range. So it's not changing that much. That point, you say that, okay, yeah, there's nothing you can do again, right? So we say the model has reached convergence. So that is when the model is complete. Yes, yes. So it feels like, but in this case, there are methods. The gradient, so you're very right, Professor Henry. You're very right. Gradient descent, the only difference, there's another method. So people, this optimization, one of the most popular algorithms that are used to optimize the M and B to reduce the error is what we call gradient descent. Gradient descent is more mathematical. So it's more, it's not very random. It's not a random approach. It's very, it has, it's mathematical. So it has a way it does it, right? However, there are other optimization algorithms. So later on, when you're doing your continuous professional development, you discover that some people use different optimization algorithms and not gradient descent that is more heuristic, like gambling. So they just randomly change M and B until they get the best performance. Others use what we call gradient descent, which is more a targeted approach. It's more mathematical. You'll be using derivatives to direct. So you'll be directing how M and B will be changing. You will know the effects of M and B beforehand, and so on and so forth. But there are also more heuristic approaches where it's actually a gamble. You just have a large space of M and B. You try all the values in that large space to see which combination of M and B gives you the lowest error. So there are different optimization algorithms, and that's very important, Henry. You have really, so even though I'm teaching about gradient descent, know that people can use different optimization algorithms. So what you need to understand is that irrespective of the optimization algorithm, whether it's gradient descent or it's a heuristic approach, the aim is to get the least error. So that said, I think it's everyone will agree with me that it's time to just have a Q&A. So we just have a Q&A, have a break, then we continue. And hope things are becoming clear what machine learning is and what actually goes on in a machine learning model. So a machine learning model is not magic. It's just a mathematical equation looking at using the numbers in the data. And that's why you always remember I told you all those categorical things we found, like type of houses. We saw 2-story houses, 3-story houses. You are now seeing why we must convert them to numbers. Because if we're using mathematical equation, there's no way to insert a category like that story 2 into this equation. That is why we will learn that before we start machine learning, we must convert all our categories to numbers because the model is actually mathematical. And you also learn there are other models which are not mathematical, which are what we call non-parametric models. So decision trees are non-parametric models. So they will not go through this gradient descent approach. They'll go through another approach, which I will teach. Most other models like neural networks and more complex machine learning are mathematical equations. And we have parametric models and we have non-parametric models. Non-parametric is when we are not using this equation. We are using what we call a tree structure, which I'll teach you. And parametric is when we are trying to optimize these parameters. The M and B is what we call the models parameter. We're trying to look for the best parameter values that can predict the outcome. So yes, we'll go now. So I'll just have a Q&A so that after this, we'll take a 10 minutes break and before we move on. So the first Q&A question is, what is the initial step in the model training process? C, initialize a model with initial values for its parameters. Exactly. So obviously, this is not, remember the initial values can be any value, it can be random values. Some people have created, and that is where data scientists come into play. Data scientists are the people who are creating these algorithms. Data analysts are just using this algorithm, but data scientists are going deeper into the mathematics and creating this algorithm. So people have different algorithms where instead of just initializing it with a random number, they use a more informed way to get a better start initial value rather than just a random number. So these are what you see people saying they're doing a PhD. This is what we do as a PhD, right? We are trying to find better ways to optimize, to create new algorithms, to do things in the more to get better performance. So sometimes it will be random. Someone you hear version 3 of someone's model is no longer random, but the concept is initializing the model with initial values. What does error represent in machine learning? See, the difference between the model's predicted values and the actual values from the data set. Perfect. Why is the error of machine learning models initially large after computing the predictions? The initial guess for the model's function does not closely match the actual data. The model's parameters are already optimized. The predictions are exactly equal to the actual. The sum, yes. Obviously, because it's an initial guess, because random, right? Most likely it will hardly be close to the actual value because it's an initial guess. And that's why the model now has to go through what we call optimization to ensure that those parameters now get closer to the actual data. What happens when the model reaches convergence? So what happens exactly is A. So I think Henry got it right, but Patrick, you are also correct. That is what you would do. So what happens when the model reaches convergence is the model it will randomly adjust its parameters. But anyway, I'm actually wrong in that because as I mentioned, it can be random and it can be intelligently, right? So let's assume A in the sense that it would adjust its parameters. So let's remove that word randomly. It will adjust its parameters without reducing the error. So the error will not go any further. And yes, okay, sorry. So I even had the correct because it's not random, right? So C is the correct answer. So further adjustments of the parameters make insignificant improvements. So C is the correct answer. A would have been correct if we removed that randomly adjust because it doesn't in all scenarios do a random adjustment. D is correct because you will stop at this point, you will stop trying to predict. You will say, okay, you will start using the model, right? So you stop prediction after the convergence after the model has reached convergence. So that said, we'll have a 10 minutes break and we'll resume at 5 past 12. And hope you guys enjoyed. If you have any questions, please let me know. We will now start with what we call the training and the test data sets. So let me know if you have any questions, get a glass of water, walk around, and we'll resume at 5 past 10. Thank you. I'll stop recording.